Let's find the trajectory of a rider on a 2-kilometer long zip line. In this case, the mass of the cable is going to be much greater than the mass of the rider. So we reduce this problem to a related problem of finding the shape of a cable hanging under its own mass. So this is the real problem that we're going to solve. Here I've drawn it from the same level, but actually it doesn't matter. The model that we find is going to be independent of where these two ends are placed. So now I'm going to draw a short segment of this hanging cable and choose some coordinates to make solving this problem a bit easier for us. So here's a segment, and I call this point at the bottom 0, 0. This is the origin of my coordinate system, and this is where the cable is at its lowest, the minimum, where the tangent is horizontal. And then this coordinate here is the point xy. Note that I've chosen to draw the right half because this curve is going to be symmetric about the origin because it's an even curve. So I only need to model the right half. To describe the shape, I want to find y as a function of x. That is, it's my goal to describe the curve as a function y equals f of x. What you're going to see is that by trying to describe the shape, what we're going to come up with is a differential equation. So let's get started. To model this, I'm going to do a force balance. That is, I'm using Newton's equation F equals ma, and I'm going to find all the forces acting on this segment of cable. First of all, there's the force due to gravity, which pulls down with magnitude mg. But what's the mass? Typically, we are given the linear density lambda of a cable. This is something we can look up in a table, or it's given to us. It's a property of the cable. So the mass is this linear density times the arc length of the cable between these 2 points. Let's call this arc length S. I don't have a formula for S, so I've actually just introduced a new variable, but we know this new variable should somehow depend on x and y. So now I can write the magnitude of the force due to gravity as lambda g times S. If we assume that the cable is inextensible, that is, it doesn't change in length, the only other forces are tension forces that act along the cable and are tangent to the curve. So there's a tension force in the horizontal direction at the point 0, 0, which has magnitude T sub 0, and a tension force at the point xy, tangent to the curve at this point, with magnitude T. To describe the direction of this tension force, T, I'm going to introduce a new variable, theta. Theta is the angle between the horizontal and the tangent to this curve at the point xy. That is, theta depends on this position xy along the curve. Because the cable is hanging statically, that is, it isn't moving, the acceleration is 0. So these forces must balance. In other words, F equals ma is equal to 0. We can describe this force balance in terms of 2 equations. One balancing the forces in the y direction, and one balancing the forces in the x direction. Balancing the vertical forces, we find that the force due to gravity is equal to the component of the tension force T that points along the y direction. And this component is given by T sine theta, this vector here. So lambda Sg, the force due to gravity, is equal to T sine theta, the vertical component of this tension force. Balancing horizontal forces, we find that T0 is equal to the magnitude of the component of the tension force T that points in the horizontal direction, and this is given by T cosine theta. This equation T0 is equal to T cosine theta is telling us something physical. It's actually telling us that the horizontal component of the tension is constant along our entire cable. At any position, the horizontal component is the same. So now I'm going to do something that's a little bit tricky, which is that I'm going to divide these 2 equations. This cancels out the tension force T and leaves me with one equation. Lambda g over T sub 0 times S is equal to tan theta. Before we go any further, I'm going to clean this equation up a bit. Note that lambda, g, and T sub 0 are all constants. So I can collect all of these constants into a new constant that I'm going to call 1 over a. The key thing to note is that a is determined by the setup of the zip line, or hanging cable in this case. It depends on the initial horizontal component of tension, which we know to be constant throughout our cable, the linear density of the cable, and gravity, which doesn't change on Earth, but might if we try to build a zip line on Mars or the Moon. So now I have the variable s as a function of theta. So in some sense, I'm done, but of course, I'm really looking for y as a function of x. To do this, we need to describe s and tan theta in terms of x and y. So I want you to go ahead and give some thought as to what tan theta is by thinking about it geometrically and mathematically in the next problem, and then we'll be back to finish modeling this curve and find a differential equation that describes this shape.